Given two frames of point clouds, our target is to establish correspondences between them. A typical solution is via geometry description. More specifically, raw geometry is projected into the feature space, where the corresponding points are much closer to the non-corresponding ones. By matching the nearest descriptors, correspondences can be established. We consider both the rotation invariance and the feature discriminativeness. Our input is a pair of point clouds P and Q, which is first forwarded to our designed encoder. For rotation invariance, we design a point pair feature-based local coordinate system, and for discriminativeness, we introduce a novel self-attention mechanism based on it. Upon that, an encoder architecture is proposed for pose-agnostic geometry description, and it is built fully attention-based for a more representative geometry learning. Then the encoded local geometry flows to the aggregation stage, where the pose-agnostic global position representation is learned, and the global context is aggregated in the position-aware fashion. This work is motivated by the trade-offs between the intrinsic rotation invariance and feature discriminativeness. For the rotation invariance, those non-learning-based handcrafted descriptors guarantee it by design. That means given a point cloud P and a point of interest, by adding an arbitrary rotation R on it, the geometric descriptor in the feature space should be unchanged. Although recent deep models learn more powerful descriptors, most of them neglect this property. For the same case, the rotation invariance is not guaranteed, and it must be obtained via augmented training, which makes their descriptor sensitive to rotations. There are also some deep models that are designed to guarantee the rotation invariance. However, they suffer from their non-discriminative geometry description. That means, given a point cloud P and a point of interest, and a non-corresponding point in point cloud Q with similar geometry, existing rotation invariant deep models project them to similar descriptors which are hard to distinguish. More specifically, for the design pipeline, we contribute both on the local and global level of geometry description. For the local level, we introduce a novel encoder architecture. We stack several encoder blocks in our encoder design, and each of them contains an attentional aggregation layer that encodes the local geometry around downsampled superpoints and a point pair feature attention layer that exchanges context among adjacent superpoints. Both layers are built upon our proposed point pair feature attention mechanism. Different to the standard attention that only fuses the learned context, and the geometric transformer attention that only leverages geometric cues for reweighting the attention, we propose to encode the raw geometry for the attentional aggregation. For the global aggregation part, we propose a novel transformer architecture for the global aggregation. More specifically, it stacks several global transformer blocks, each with a self-attention module and a cross-attention module. The self-attention module consumes both the learned local descriptors and raw 3D positions. It has two branches, where the context branch takes charge of context aggregation, while the geometry branch leverages the raw 3D positions to learn a rotation invariant global position representation. The cross-attention module takes both the fused context and the rotation invariant global position representation and fuse cross-frame information in a position-aware manner. Here we show the results. The x-axis is the feature metric we call on 3D low match, while the y-axis is the same metric with enlarged rotations. For previous methods, those rotation-sensitive ones learn more discriminative descriptors, demonstrated as the rightmost scatters, while the rotation-invariant ones are more robust against enlarged rotations, shown as being closer to the diagonal. Our method possesses the advantages from both sides. It has the most discriminative descriptors and the best robustness against rotations. Here we show the experimental results on the indoor scenes. Quantitatively, in terms of both the feature metric recall and inline ratio that evaluate the matching quality directly, we achieved the state-of-the-art performance on the original 3D match and 3D low match benchmarks. When the rotations are enlarged at inference time, our superiority of being intrinsically rotation invariant becomes more significant. Qualitatively, on 3D low match, we extract more inlier correspondences compared with GeoTransformer that is a state-of-the-art method. Our method also has the state-of-the-art performance in non-rigid matching scenarios. Compared to the state-of-the-art method for non-rigid matching, our method could extract better correspondences. Thanks for the watching. For more details, please refer to our paper and code.